Hi everyone, my name is Matthew Rocklin. I work for Continuum Analytics. I assume everyone knows what Continuum Analytics is, but just in case, it's a for-profit company inside the open source scientific Python ecosystem. In particular, they make Anaconda, so the people who are sort of outside. I'm here with Phil Cloud here. Phil, can you raise your hand? If you have questions like my laptop doesn't work, please go and grab Phil. If you have questions like, philosophically, how would this affect my workflow, then please direct that to me, or direct any question anywhere you want. So there is a GitHub repository at this location. Let's just go and. So if you go to that location, there's a repository. This repository has some notebooks in there. The notebooks have some prose to explain things. They also have some brief exercises. There's also some small data sets and some scripts to sort of make them much larger data sets. So what you should do relatively quickly if you can is download that repository. It should be a few megabytes. And then run this script, this prep.py script. And that's going to make some artificial data. That's going to expand out artificially some small data sets. That's if you want to follow along and do some exercises. How this tutorial will work, there will be sort of maybe 15 minutes or so of me chatting at you while those scripts run. And there'll be a series of notebooks. Those notebooks will include, again, some explanatory prose. They'll also include some brief exercises just to make sure that you have your head in the game. Okay, any questions? Can I move away from this slide? Raise your hand if I can't yet move. Okay, there's only one of you. Neither of your neighbors have raised your hands. I'll wait just a second. And we're gone. Okay, so we're at the PyData conference. And PyData is largely a software community based around, I'm going to claim, two data structures. The NumPy ndarray, an n-dimensional array, and the Pandas data frame, a sort of in-memory relational database table. The fact that we all depend on these two data structures makes it so that all of our libraries interoperate very effectively. Right? We've got all these libraries. We've got plotting libraries. We have data loading libraries. We have analysis libraries. And they all can interoperate without having to communicate to each other pretty much at all. Different teams can work independently, and yet all of the users can use all the libraries together. This has been really effective. However, both of these libraries have two main flaws. One, they're mostly limited to data that lives in memory. And two, they mostly use a single core. And as we have data sets that grow large, as we have hard disks that become faster, we sort of want data structures that can reach outside of memory. So use the 200 gigabytes on my hard disk rather than the 16 gigabytes on my memory. And as our laptops grow to many, many cores, this laptop is a very old laptop. It's maybe 3 or 4 years old. It has 4 cores in it. We sort of also want to use all of those. And so sort of the PyData ecosystem sort of struggles a little bit under this sort of increasing imbalance between our data structures and changes in hardware. So Dask is a library for parallel computing on larger than memory data. Today I'm mostly going to focus on using your laptop effectively, not on big data distributed computing. So I'm focused on sort of data sets that are less than a terabyte, but maybe larger than a gigabyte. So how does Dask work? So Dask was originally designed to be a out-of-core parallel n-dimensional array library. We'll talk about what that means in a minute. But it sort of has grown a bit beyond that. So there's two ways of interacting with Dask. Interact with Dask at a high level, sort of like there's a NumPy sort of mimic project called Dask Array. There's a project that mimics pandas called dask.dataframe. There's a project that mimics sort of a parallel Python list called Dask bag. And so this is sort of the high-level way of interacting with Dask. However, all of these systems all rely on the same low-level technology, which is a dynamic, low-latency task scheduler that is aware of memory. And I'll explain what all those things mean again also. So we're going to talk about both of these two things at the same time. We're going to jump between the high and the low level today. We're going to play with sort of a pandas-like thing that does sort of high-level operations. And we're going to dive down and see what's actually happening to make all of those things possible. Okay. So very briefly, so we sort of want to write code like up here. Here's sort of a mock of what you might write in a NumPy computation. Some matrix multiply, some mean across some dimension. Or maybe if you're doing some sort of pandas operations, you might use group by operations with aggregations. And so what Dask does is it uses this exact same syntax, so it's a drop-in replacement for NumPy, and it's going to turn that into a sort of recipe, a bunch of different tasks to run. If you're here for the Luigi talk in this room directly before this, Luigi is also a task scheduler, but more for sort of big data processing pipelines. We're going to do the exact same thing, but a much finer grain and at a much quicker timescale. So Dask Array and dask.dataframe will turn code that looks like these two lines into these sort of recipes, a bunch of different small functions to run in memory. And we'll talk about these graphs in a minute. And then the Dask schedulers will execute these graphs in parallel, using many cores, either many threads, many processes, or many machines in a distributed cluster. That's sort of the high to low level transformation we're going to walk through. So again, the general goals of the tutorial, we're going to learn to use, at the high level, Dask Array, dask.dataframe, dask.bag, these sort of copies of NumPy and Pandas in the Python list, to operate on inconveniently large, but still doable data sets on our laptops. Okay. At a low level, we'll learn about dynamic task scheduling and how that might be a decent way to think about parallelism on more custom workloads. What I found when dealing with Dask Array, dask.dataframe, dask.bag is that actually a lot of problems I wanted to do didn't fit easily into any of those abstractions. And so we need sort of a release valve, a way to talk about other kinds of workflows that don't fit neatly into pandas. Okay. So we're going to jump between high-level collections and low-level scheduling in these different sections. And each of these different sections correspond to a couple of notebooks. So again, you should have downloaded a GitHub repository that has those notebooks. If at any time I'm just droning on and you want to just totally forget about me, I highly recommend going through those notebooks at your own speed. Some of these will be interesting to you and not interesting you. So it's nice to buffer that. Okay. So we're going to start with Dask Array. And so this is this notebook. Okay. I'm going to go through a bit of this with slides, and that'll sort of overlap a little bit with the first bit of prose. Then we're just going to switch straight into notebook. Okay. Yeah. So Dask Array is, again, an out-of-core, multi-core, n-dimensional array library that copies the NumPy interface using blocked algorithms and task scheduling. So let's talk. I'm going to switch between. So is this text readable in the back, or should it be expanded? Yeah, OK. So I assume people here are familiar with the NumPy interface. So there's another, so Dask Array has a sort of a similar looking interface. Okay, so all the sort of subset of the functions you're familiar with are there. Okay. And we can do things like make a random array of normal variables with mean 10 and standard deviation 1. It'll be a relatively large array. And we're going to supply also a chunk size. So this bit is straight from NumPy. That's valid NumPy. And this bit we're adding adds a little bit of information telling how to break up our large array into lots of little smaller arrays. Cool. I can lift up the window. Yeah. Is that the question you had also? Great, thank you. Thank you for being loud. And so this is going to do some work, and we're going to call compute on that. That's going to go. And we're going to see my little 4-core laptop churn on that large computation, making all those random variables. Oh, wait, hold on. This is bad. This is very bad. Yeah. Notice my memory just went up to 70% there, right? It almost just crashed my machine. Let's compute the mean of that. That'll be much friendlier. So it'll actually be, whoops, I want DA dot. There we go. Let's see this guy again. Okay, this is what I wanted to show. What I wanted to show is that we're using all of the cores and a very small amount of space to compute something that's actually fairly large. And then we computed the answer and we're done. So if you watched top here, this top line, CPU is 300, 400%, but memory usage is very small. And that's sort of the general trend that we're shooting for. This is ideal. Shooting for maximum CPU usage, but very small amount of space on easy to write down computations. Okay. Now, this computation you could do in many ways. Okay? You could do it just with iterators, walking through and computing this thing lazily. You might actually think about, wait, how would I compute the mean of 200 million numbers? Or a trillion numbers? How do I compute that mean? Right, if I gave you an array, how would you do it? So here's how we might compute the sum of a trillion element array on disk. Okay. So we might have, let's say, a big HDF5 file, a big just NumPy array on disk effectively. We have a trillion numbers there. What we're going to do is we're going to take out one 1 million size chunk, take its sum, store the result. Take out another million size chunk, take its sum, store the result. We do this 1 million times. Then we're going to have 1 million small sums. We're going to take all of those together and then sum them. And so we can compute the sum of the entire array by computing 1,000,001 small sums. Okay. And we can use NumPy, just the normal NumPy library, in memory on each of those sums. So we're still very fast. This is effectively what Dask does all the time. Question?
Does Dask typically serialize with using HDF?
Question is, does Dask usually serialize?
Yeah, which format do you use to serialize? Is that HDF or your own?
Yeah, the question is, how does Dask serialize data? So how do we serialize data in this example? We're just pulling stuff off of HDF5. That's just bytes coming off. NumPy and H5 knows how to interact with that very, very cleanly. There's actually no unnecessary serialization that's happening here, as long as we do this in a streaming way. Right? So there's actually no excess serialization. There's no excess cost. This operating is actually running at about peak efficiency, except that this is running sequentially. We could do this in parallel. So Dask will do effectively this for loop, but in parallel. Does that answer your question?
I would actually want to know, how does it serialize when necessary?
That would depend on the different kinds of things. But let me get to that later. Okay. So this brings us to our first exercise. So again, you guys have a little bit of work here today. If you want to sort of ignore the exercises, feel free. I'm not your teacher, unfortunately, or fortunately, depending on. Yeah. But if you walk through this notebook, let's make some vertical space. So this first notebook is notebook 1. There's some links to some documentation. There's some things I've already said. If you don't already have, so if you ran the prep script, this first array should have been already stored on your computer by now. It should be, I think it's about 1 billion numbers, just random numbers. They're not very interesting. And here's our little script in a smaller scale. So we're going to run this exact same thing we just talked about, just a for loop running over an HDF5 file, and we're going to compute some very large sum. And so your job is to compute the exact same thing, but instead of computing the sum, compute the mean. And again, not using Dask, we're just using NumPy and for loops. So there's just nothing you haven't seen before. And there's a little algorithm there that's going to say how to compute the mean by computing both the sum of each chunk and the size of each chunk. Then we're going to add up all of the sums, we're going to add up all of the lengths, and we're going to divide the two by each other. In this case, we could sort of do it more efficiently, more quickly, but this algorithm happens to be general if you don't know the size of your chunks ahead of time, which happens a fair amount. And so the first exercise, again, spend 60 seconds on this, don't work on it too hard, is sort of copy and paste the code above, but extend it to compute the mean instead of the sum. I'm going to sit here and enjoy you all for a moment. And then if you want to check your answer, you can use, so the Jupyter notebooks have this little load magic, and you can just run that cell, and that'll bring in the answer from a directory that's in your repository. just so I can get a sense of participation, if you're still actively working on this, can you please raise your hand? If you were working on it and have finished, can you raise your hand? And please be honest, if you have no intention of doing exercises, raise your hand. This is usually me in tutorials, so it's totally fine to raise your hand here. Okay, great. Thank you. Okay, I'm gonna move on, and it won't conflict with the work you're doing. So you can also think about not just these simple algorithms like computing the sum or computing the mean, but oftentimes a lot of array operations actually can be blocked up in the same way. For example, it's a very common exercise in an algorithms course, in the linear algebra course, in mathematics, think about blocked matrix multiply. The fastest way to multiply two matrices is often to do it in many small blocks. This is actually better for cache performance. And that algorithm actually looks a whole lot like normal matrix multiply. And so there's a large collection of blocked algorithms that work very well in arrays. This has been sort of well established by the linear algebra community. They've done this for decades on fast linear algebra libraries. And we're taking those same techniques and applying it to more general sort of pedestrian n-dimensional array use cases. So to demonstrate that, one more thing. So when we did this loop, we didn't need the for loop. The for loop says do this one thing, then do this other thing, then do this other thing in exactly that order. We actually wouldn't have minded doing those in parallel. Computing these sums, computing these means, those can be done in parallel. And so we're going to represent our computations as these graphs, where at the bottom we're going to have some data and little things are going to percolate up. This will make a lot more sense in just a minute. When I give a talk, this is sort of the more fun part of the talk. So we're seeing sort of the bit of a talk, and then we'll switch a bit more to, there we go. So this is in order to give you some intuition on blocked algorithms. And again, you've just been doing blocked algorithms when you computed that mean. You computed a big thing by computing a lot of little small things in memory. Okay. So we're going to make an array of ones. And that array of 15 ones will be cut into 3 blocks, each of chunk size 5. Okay? And then we're just going to look at what that looks like. If you do this at home, you can do it in your notebook right now. If you have the GraphViz library installed, GraphViz is both a system library that you'd have to install through your system manager, brew, apt-get, some double-click installer through Windows, and it's also a Python library. You have to pip install. Okay. Once you do that, oops, there's my little graph. Okay, so how we decode these graphs is as follows. All of the circles are functions, usually NumPy functions. So Dask Array is making a graph with a bunch of NumPy functions in it. And all of the boxes are arrays, usually NumPy arrays. Okay, and flow goes up. So we're calling ones 3 times to make 3 different NumPy arrays. And that's going to create 3 NumPy arrays that just live just above. And if we do something like, let's say, add 1 to our array, then our graph is going to change. And we have to do 1 operation on each of our little boxes. Okay. And if we do some other sort of embarrassingly parallel operation, our graph is going to go even more. Okay. If we do something, let's say, take the sum, we're going to, for each array, we're going to make it with ones. We're going to add 1 to it. We're going to call NumPy sum on that array. We're going to do that for all of our 3 arrays. We're going to bring them all together and do 1 final sum. Okay. So these graphs are intended to give you some intuition about how blocked algorithms work, sort of what you just did with the mean computation. Okay. This is going to get much more fun when we start doing more exciting array computations. Like let's do some slicing. Or when we go to n dimensions. So I'm going to make a 15 by 15 array that's cut into 9 chunks. Each of the chunks is of size 5. 5 by 5. So there's 9 little arrays there. We can do our sort of old tricks, like adding 1 to all of them or computing the sum. And you can see here again how reductions look like. Right, reductions do some operation and they bring everything together and do some other operation. This gets more fun again. We start thinking about operations that are sort of dimensional in nature. These graphs start to expand and start to contort to look more interesting. So for example, we can look at what x plus x transpose looks like. And you might want to think about in your head, how do I expect x plus x transpose to look like? All these different blocks. I'm going to take one array and then sort of flip it around and add them together. So some of those blocks are going to interact with each other. Right, and it gets sort of fun. There's some interactions between different parts. So over here we see blocks that are on the diagonal and they interact with themselves. And here we see blocks that are sort of off diagonal. They interact with some other block. Let's just start doing some more fun things here. We take a matrix multiply with the transpose in there. Let's add 1 just for color. And let's zoom this out. Maybe we'll subtract the mean along some axis. And then take the standard deviation. Okay, there we go. Okay, so these are blocked algorithms. Okay. Questions on this so far? Someone give me a question. Yes?
When you call sum, there's the intermediate sum where it sums each block.
Mm-hmm.
That's something that you put in for task. So you know that the sum of the sums is the same as the sum of all the elements. So you kind of tell that? Is that right?
Right, so the question is sort of how do we write these graphs, maybe? For example, when we think about the sum, we know that's a sum on each block preceded by another sum on everything. So yes, so that's what is in the Dask Array code. The Dask Array code is effectively a lot of little recipes that write down these graphs. And dask.sum involves lots of little NumPy sums. Dask.mean involves both some NumPy sums and some counts in there. And dask.standard deviation looks a little bit stranger. Dask.dot involves lots of NumPy dots. So yes, that's something that is inside the Dask Array library. That's what Dask Array library brings to the table. Now, once we, yeah?
I have a very similar question. So it looks like when you call sum, if they're called, if you sum on each chunk, and you sum them together.
Right.
One call, yeah. You find situations like just because you move memory around in such a way that that becomes an expensive task where it would make sense to keep the memory, like the operations close to where the data is. So like basically sum over the chunks and not do the second sum.
So your question,
When you call
what?
sum, it basically does two sums, right? It sums inside the chunks and then it sums over the chunks. And like, I don't know, my personal experience has been whenever you basically have to aggregate something across all the various nodes, that becomes a bottleneck. So I was wondering if like.
Right, so in this case, we're going to take, if our goal is to sum a large array, we're going to take the sum of each chunk. The results of those sums will be quite small. And we can hold on to those, we can move them around, they're cheap. However, let's say we're going to take a sum and do a mean in the future. We might want to sort of hold on to some data in order to avoid spilling down to disk, in order to avoid having to load it back up again, in order to avoid communication. And so it's very, very important, even though we've written down this graph, we haven't necessarily specified the order in which things happen, nor have we specified communication if we're thinking about distributed computing. So this graph is sort of separate. This graph is sort of a recipe. But we actually, if we have sort of one chef walking through this graph, we're not sure in which order that chef is going to do things, and if they're going to hold on to intermediate results or not hold on to them, et cetera. So does that sort of open up your question?
Yeah, exactly.
Okay.
So we'll talk about scheduling later.
Yeah, and so the question is, so we've written down this graph. Wait, we actually wanted an answer out, right? So with Dask Array, one strong difference between the interface of Dask Array, so everything here should look familiar to NumPy users. I should bring this up higher. Everything here should look familiar to NumPy users. When we actually want to eventually compute a final result, we need to call compute, and we get out a result. Okay. And so when we called compute, 4 threads, because I have four processors, just walked through this graph, calling all of our functions, making little arrays, and calling the other functions. That happened in a relatively short time. It's a very small data set, but it happened in 55 milliseconds. So Dask internally, there's the little thing that's actually executing all these functions. That is a low latency dynamic scheduler. that it's very memory aware. Today, I'm mostly going to talk about single machine parallelism, in which case we don't care too much about communication. And the academic work behind Dask is all about memory-aware dynamic scheduling. It's about making those choices about walking through that graph in just such a way that we had a low memory profile, stored results that we should have stored, and didn't store results that we shouldn't have stored. So the question you brought up is very, very central to making this run well. I'm not going to talk too much about the algorithms involved in that, because that's sort of a separate talk. But this is sort of maybe a theme for today. We're going to make these graphs, and we're going to execute them. And we're going to learn about both how to use this syntax, the sort of NumPy stuff, plus the sort of administrative bits, like you have to call compute at the end. That's something that we need to learn. And we'll learn about sort of the graphs in general and how they're built and how we can use them for more custom workloads. We'll then do the same thing for pandas. Okay. So, really great questions, by the way. I really appreciate. Questions make a presenter's life so much easier. They're far more interesting than me talking. Okay, so here was my solution to compute the mean in chunks. This is something like what Dask does internally. Okay, so again, we sort of have this general idea. Dask sort of looks like NumPy. It makes these graphs, it computes them, great. Now how do I actually interact with real data? Wait, I actually have a data set. I have an HDF5 somewhere. Actually, I probably have 100 HDF5 files somewhere. How do I actually have Dask operate on that data in an intelligent way? Okay, this is sort of the tutorial part of the tutorial. So we usually import Dask Array. Let's expand this a little bit. As DA by convention. And there's a da.fromArray function. This function will accept anything that accepts NumPy slicing. Anything where I can say that object, bracket, put a slice, and get out a NumPy array. This is true of H5 PyDatasets. This is true of PyTables datasets. This is true of bcalls. This is true of netcdf files. They all provide some interface whereby, so I have this dset object, which you do too, which is an H5Py object. It's a sort of a pointer to a file on disk. And I can use this dset to pull out some chunk of my array. That returns a NumPy object. This is H5Py. It's a great library for interacting with HDF5. It's a fine library to deal with data on disk. It's very efficient. So we have made this large array of data, which you've been playing with. This is what you computed your mean over. And we can create a Dask array on top of this array with the fromArray function. That takes any object that supports slicing with a chunks argument. So you need to specify the size of block that you want to pull out of that array at any given time. If those blocks are too small, then the latency of the scheduler will hurt you. If those blocks are too big, they won't fit in memory. I usually shoot for blocks that are around a megabyte to 10 megabytes in size. Okay. So here, we're going to turn this HDF5 file into a Dask array. We haven't loaded anything yet. This is just created a little graph with a lot of functions that load data from that HDF5 file if we need them. Okay. And now once we have this Dask array, this is what it looks like. So here's the array. We could visualize it if we wanted to, just be a bunch of sort of flat tasks. And we can compute things on it. We can call sum. And when we call things like x.sum, remember that hasn't done any work yet. It's just made a graph with a lot of little sum calls, followed by another sum call. If we actually want the result, we need to call compute. So compute is a method on any Dask array, or on any dask.dataframe, any Dask bag, that says, okay, I'm ready now for you to do work. Please execute all the stuff I've mentioned so far and do it in parallel. So we get a result back. And ideally, this is the same result that we computed earlier. So your new exercise is the same as your old exercise, to compute the mean of this large file on disk. Before you did it with for loops, this time do it with Dask array. This should be relatively easy to do, just with the mean method. I'm going to wait 10 seconds, or 20 seconds.
So how
far were you able to extend this into other NumPy linear algebra functions like least squares and that sort of thing?
Yeah, so actually it's great to intermix questions with exercises. That's a great idea. So the question is, how far does Dask Array go? Right, so first of all, total disclaimer, Dask Array does not fully implement NumPy. NumPy is a large interface to implement. Dask Array does not even try to implement all of it. It does implement a surprisingly large subset. Like I did not expect it to be as easy as it was. And so if you go to the Dask docs, that's dask.pydata.org, you can go to the overview, and here are the things that Dask Array implements. It's most elementary operations, slicing, which is interesting to do, reductions, things like tensor dot, transpose, a lot of sort of random things people have asked for. They're actually it's pretty easy to implement most of these things. There's sort of this broad class of operations in NumPy that just are sometimes used, and they get implemented as people ask for them. Things specifically Dask does not do is dask.linalg, because you should really be using an optimized BLAS library for that. And also any operation where we can't infer the shape. I'll talk about that in a moment. But there's a class of operation that Dask Array can't do. But more generally, there are documentation that talks very strictly about limitations. OK, so we're going to compute the mean. Remember, before we had this for loop that walked over our data in chunks. And now we're going to say x.mean. OK. And so this is going to do all of that chunking for us. It's going to execute in parallel. So if I bring up top, it's only actually one thing. Oh, we are probably I/O bound on H5Py. So threads aren't giving us much here. But the average is about 1. Yeah, question?
Yeah, that's actually my question. I mean, if that the dependency graph is created closely matches the actual execution plan, or how Dask actually honors the query, then you'll end up with a lot of parallel I/O, which might actually be worse than reading each chunk, updating some, moving on to the next chunk. So how does it handle that? Does it change the execution plan dynamically?
Yeah, so the question is, if I look at this graph, for example, I don't want to load up all of our data and then run something. I might actually prefer to load up one piece of data and execute it to completion, and load up another piece of data and execute it to completion, because this is better for I/O. I actually claim this is also better for memory storage. I don't want to load a whole data set in memory. That defeats performance entirely. So you mentioned the question, how do you honor this while also being efficient? But I claim that this hasn't specified an order at all. I'm actually entirely free to select my own order. And the order in which I run tasks is entirely sort of the magic behind the Dask scheduler. So this particular workload will run like this. Blue things are finished or released. Red things are occupying some resource. So blue circles are functions that have run. Blue boxes are data that we've seen, used, and released from memory. Red circles are occupying a thread. They're being run on by a thread. Red boxes are occupying memory. And what you'll notice is exactly the same flow that you just mentioned. You want to sort of go vertically in order both to optimize for I/O and also to minimize memory footprint. Does that answer your question? Yeah. And making these choices, especially on complex graphs, in 1 millisecond of time is, again, sort of the hard thing behind the Dask schedulers. And that's sort of the magic that they provide. And we'll talk about the schedulers more in a while, although not as in depth as we perhaps could. OK, so if you want to sort of compare parallelism, this is a nice example. This is an example very similar to what we did originally. Just create a random array, compute some mean on it. My laptop that I have here has only 4 gigabytes of memory, so I actually can't run that computation with NumPy. But if I go to a machine with more memory, I can actually do a comparison. And Dask Array runs faster. So it's not only out of core. Not only can I run this computation with Dask, but it also gives me multi-core. I can run this with many threads. When many threads can be used, that's not always useful. But if you feel like benchmarking something on your own system, try this out. And again, if you have a decent amount of memory, or maybe you can sort of for NumPy, or you maybe shrink down the problem size if you want to play with NumPy. Most people that I've talked to have been much more excited about the out-of-core nature. When I say out-of-core, I mean uses disk well, and doesn't fill up memory. That's what I mean when I say out of core. People tend to be more excited about that, about the possibility that allows, rather than multi-core, getting sort of a 4x speed up. Great, and there's people who care about multi-core too. There's lots of, people use arrays for lots of things, it turns out. Okay, so fun exercise. You have a weather data set, which, this is most of what you downloaded, was about 3 megabytes of weather data. That script that you ran expanded out to 2 or 4 gigabytes of data using SciPy IMRI size. So we have some data in here. We have some very large files. This is the weather, I think, in January of 2014, 2013. And we're just going to look at a bit of that. So we have actually there's actually sort of temperature readings in there. In some units, I don't know what they are. And we're going to show that off. Oh, no. PNG. Matplotlib died. Oh, hold on. This is very unfortunate. No? Jake. I did not build Matplotlib from the source, no. I almost certainly did. No? Okay. Well, there's a very pretty picture of the Earth. No, it's okay. We're just gonna blow past this. Well, there's a very picture of the Earth and weather. It looks actually, this is great. This is why you reuse examples between. I write a blog. Most of what I'm talking about has been talked about there. Creates pictures like this. This is the picture we want to see. Picture of the weather. Okay. And the problem that we have is that inside of your directory, there is this data folder with weather big, with a bunch of HDF5 files that all hold the temperature on that day. Okay. And all those files are, not particularly big, but they're inconveniently large. And this is because it's sort of the biggest size I could possibly give to you that wasn't completely silly. So you have all these files. We want to operate on all of those files as one large Dask array that we want to slice through. Okay. So, what are we doing here? Okay, so we have all of these dataset objects. Okay, all these dset objects. This is an exercise for you. And for any given one of them, we can use the from array function, just like how we did at the top. So I'm going to do that here once. And you're being suggested to use a chunk size of 500 by 500. Okay. And that's with this chunks keyword argument. So chunks is one of the API bits for Dask Array you really need to know about. It's something you need to think about. What's the right size of my chunk that I want to use? Okay. Okay. Question is, can I set chunks globally as a configuration constant? No, you definitely can't. And I think that'd actually be a bad idea, because for different data sets, you're going to need, or different computations even, you need to use different chunks. Originally, I tried this computation with 1,000 by 1,000, my sort of normal go-to size. But at some point, we're actually going to be stacking a bunch of these things together. That actually was blowing up my memory. Again, my laptop has 4 gigabytes of memory. It's a very old machine. So I actually needed to downgrade chunks a little bit. It's not really a globally settable setting, something you need to think about. Dask Array gives you a lot. It asks you for this. It asks you to think about chunk size. So here's one Dask Array object. please make one for each of your data sets. Okay, so you have all these dset objects, which are these H5 PyData sets, dataset objects. Make a bunch of them. Then you're going to use the Dask Array.stack function, sort of very similar to the NumPy vstack function or the stack function that's coming in new NumPy. And you want to stack along the axis equals 0, so that you have an array, a Dask array, with this larger shape. So now have sort of time slices. Each of those arrays on disk now becomes one array, one slice, in one large Dask array. Then you end up slicing through that array in fun ways.
Did you mention that last LA pack do out-of-core stuff? That there were some packages for that?
The question is, did I mention that there's some out-of-core BLAS or LAPACK packages? I may have incorrectly inferred that. I'm certain that some exist. There are certainly very many parallel distributed high-performance BLAS or LAPACK libraries. That is a game that is sort of sufficiently academic and well-researched elsewhere that I try very hard not to comment on it too much. So I'm going to just take the fifth on that one. Yeah. But things like Plasma or Elemental or Flame might be at least communities that would have thought about this problem. But I won't claim any functionality or lack of functionality on any of those libraries. Okay. So once you have that big stack, so we're going to make lots of different Dask arrays. We're going to call the stack function to stack all those Dask arrays into one larger Dask array. Then we're going to put the mean across time. We're going to flatten all those back down together. Then you can just plot that. You can just dump that into matplotlib. And matplotlib will end up calling the numpy.array function on it, which will trigger computation. So hopefully your matplotlib does work, even though mine does not. And hopefully you can get out a pretty plot. Has anyone succeeded in getting a pretty plot? Yes. Okay, I should move faster. Is it pretty? Yes. Okay. And what's neat is that all that happened and could have happened on a terabyte. Notice also that when you were constructing your array, that happened very quickly. So even though you were saying, make an array and stack all these things together, you're actually playing with all of these files on disk and all these different pieces out of all those files on disk. But no actual work was ever happening. You were just making a very large, very complex graph that pulled things from the right place, stacked them together, did some computations on them, and then finally plotted. It's only when you actually hit compute or when you throw it into a function like matplotlib imshow that computation occurs. Okay. So here's my solution for that. We have all these file names. We make each of them into a data set. This was given. We're going to call from array on each of those. We're going to stack them all together. We're going to compute the mean. So all of this should look like typical NumPy. We're sort of reusing your NumPy experience. And we're going to plot them. Matplotlib apparently isn't happy with me, so I don't get much. Okay. I'm going to move on in the interest of time. But this last exercise is about storing results. So often you do some work, and that work happens, your array happens to still be out of core. You don't want to call compute, because that's going to make a NumPy array for you, and that's going to crush your system. You actually want to store that in some other out of core system. And the store function is sort of the converse of from array, where from array accepts anything that works with get item, with slicing. Store works on anything that supports slicing set item. X of bracket equals some NumPy array. So store will store large arrays in a streaming fashion. So we'll pick up some block, do some work with it, combine it with other blocks, put that block on disk again. Pick up some other blocks, do some work, take the result, put it back on disk. And again, all in a way that's respectful of memory. Okay, questions? Yeah.
When you computation results in another
So the question is, I'm gonna answer a question that may not be yours, but is maybe sometimes valuable. I have some data that actually has some local behavior, and I want to do some algorithm that runs in parallel, but is sort of respectful and aware of that local behavior. Many image processing operations have this need, or finite differencing, sort of needs to know a little bit around themselves. Is that roughly the context in which you're thinking?
Exactly.
Yeah. So there is a function in Dask. There's a sort of submodule called Dask Array.ghost. For ghost cells is a combinational term some people use. What it's going to do is that's going to take all of your arrays. It's going to sort of take all the borders of each little array and share them. It can apply some function, embarrassingly parallel, but now you have a little bit of extra stuff lying around. And then it's going to trim off the edges and give you back your result. Let's go look at, people have used this to try for things like finite differences. Turns out that the memory copies end up being prohibitive. But if you have sufficiently complex computations, it's a great solution. In particular, actually, scikit image now actually depends on Dask because of exactly this functionality. We're able to get sort of 2 to 3x speedups on a lot of their functionality. There we go. So this is sort of in pictures, this is what I was just talking about. So actually, Dask is the reason why scikit image just released the GIL, because they want to use all their algorithms in parallel using Dask and this mechanism. So here's a class of operations for which Dask Array is well suited, but is tricky to do in general. Okay, great. Okay, so I want to switch gears now. We're at the high level for a while, talking about these big NumPy arrays. I want to switch gears to low level about those graphs. This section, if you don't care at all about the internals of how Dask works, you can totally go to sleep or look at other sections or watch YouTube with headphones. So this is maybe, I just want to preface this is not essential knowledge. Yeah, question.
Maybe a selfish question, but with respect to sleeping, are we going to take a break or not?
Yeah, we could take a break. Let's. Yeah. So how long of a break would you suggest? We can do an 8-minute break. What I suggest is that we start this, and then we take a break so people can either do exercises or take a break. So give me 10 minutes. Let's shoot for 10 to 15 minutes from now, break time. Good? Great. Thank you. I'm sure your comrades in arms also thank you. Yeah. Okay, so we've seen Dask Array. It turns NumPy code into graphs. And then some magical system executes those graphs for us in parallel. Okay. But how do we actually, in Python, represent those graphs, these pictures? What's the data structure? Okay. So normally, we write down functions in Python, like these two very simple functions that increment a number and add two numbers together. And then we write down Python code. X equals 1, y equals the result of calling inc on x, z equals adding y and 10. Okay. So pictorially on the right, that's sort of one of our graphs over here. Right? I guess the arrows should be reversed here. Okay. So that's sort of the computation we were just thinking about. In Dask, we represent those computations as dictionaries. So a Dask graph, the internal representation is a Python dictionary, where each of the calls, so when we called inc on x, we can't actually call the inc function. We can't ever write down this in Python because Python will execute that function for us. We need to do something else. There's some options. We could use a string. We could put the whole thing inside of a string. We could use a partial function, partial evaluation. We chose instead to move the parenthesis from the right side of the function call to the left side of the function call, which makes it a Python tuple rather than a function call. Okay, so a Dask graph is just a dictionary of key value pairs. The values are either data or the values are Python tuples. When we're going to call a Python tuple a task, if the first element is a callable, if it's a function. And that's the spec. That's what a Dask graph is. If you can make dictionaries that look like that, all of the Dask schedulers, threaded, multiprocessing, distributed, can execute your computation. So this is the release valve. If Dask Array or dask.dataframe doesn't work for you, if you can make these dictionaries, then we can run them in parallel in an intelligent way that thinks about memory.
So it's a magic there, right? By like sorting, in this case, you can like execute scheduling this thing from top to bottom. There's some magic that goes on there, or do I have to actually write it and ensure that
Yes, the question is, well, in this way, order is top to bottom, but how do I ensure that the order that I want will actually be respected? And the answer is that you don't want to think about order. You want Dask to think about that order, because it's going to do it in parallel. But that dependencies between tasks will be maintained by the fact that this inc function has this x, and this x is also a key. And so the key value pairs between things end up determining dependencies between these different tasks. And the Dask schedules will respect those dependencies. Yeah?
A question about chunking. You had mentioned that if the goes on the values can be either data or other functions. So let's say, for instance, the value is data. In this case, would the data have already been chunked? So, for instance, if I'm going to hit the release valve myself, I need to take care of chunking.
Yes, the question is very roughly, how does chunking fit into this? Like, is the Dask scheduler going to think about chunking? Or do I, in the creation of this graph, need to think about chunking? The answer is that you, in the creation of this graph, need to think about chunking. So for example, Dask Array makes dictionaries that look like this, that already have all of the chunks already laid out. And we'll see a good example of that in a second. So I might ask, how do I run these graphs once I've made this dictionary? And the answer is with a get function. There are a few different get functions. They take a Dask graph and a key or list of keys or nested list of keys. And if you want to use processes rather than threads, use a different scheduler. There's a distributed version of this too, it's a little more complex. Okay. So I really like this as someone who targets sort of an intermediate representation. It's great to program to. I end up writing dictionary comprehensions rather than have this sort of like weird sort of DSL. There's no DSL here, it's just sort of Python objects. They're very fast. The Python dictionary and tuple are actually fairly efficient data structures. It's a little bit wonky though. Most people, unless you're sort of like a Lisp lover, really don't like writing these dictionaries. Your IDE tab completion doesn't work. There's no introspection, there's no checking of anything, it's sort of weird. Okay. So your question about chunking, this is how Dask Array runs. Right, so here, I'm going to call Dask Array.arange on 15, and that's actually going to cause 3 separate calls to NumPy arange at different sizes. So Dask Array, it's actually just a library with a bunch of functions that create and add a bunch of key value pairs to dictionaries. And the choice of those key value pairs is intelligent in some way. Okay, so Dask Array was a nice way to make dictionaries, and Dask core is a nice way to make libraries like Dask Array. Okay, or we can use it in custom workloads. So in particular, when making Dask Array, I needed some mechanism to write down my parallel operations. This is actually just a nice slide, totally outside of Dask. Here's a bunch of choices that you have. There's many others I've omitted. But here's a subclass. At the top, we have sort of very explicit, I am in control, I want to specify exactly what happens where. Libraries. This is very good for high performance. Let me control exactly what I want to do. At the bottom, we have things that I don't want to handle control. I want you to handle it for me. But they're fairly restrictive to program in. I can't specify a lot of things. They also tend to have highish latency. Dask, I needed this inside the middle. That's sort of where Dask lives. It's fairly low latency. It gives you a fair amount of control, but also takes away a lot of things that I think you don't want to have when thinking about large systems. So it lives sort of in between these classes of parallel libraries. Good example of this, there's an excellent postdoc at Duke in applied math, or maybe just math, who works on SVD algorithms, or non-native matrix factorizations is his topic. And he actually added the SVD implementation side of Dask Array, lenalg. And this is his graph. It's a very nice algorithm. This is the dictionary that makes that graph. It's sort of very wonky. There's some interesting things here. Okay. And this is sort of the thing that it would be very hard to do either with pure threading or with something like Hadoop Spark. You needed much more customization than Hadoop Spark give to you. We also didn't want to write all of that down explicitly with threads. This is a nice example showing the Dask parallel profiler and bokeh. It's a nice bokeh app. You can see there's lots of QR decompositions. There's then one very large QR decomposition, so it's not entirely parallel. There's a lot of matrix multiplies. There's work by Jim Christ. So this genomics researcher came to the Dask mailing and said, hey, this SVD is great, but I want the randomized version that I see in scikit-learn, but also out of core. Like both of those two would be great. And so Mariano went ahead and implemented this sort of famous-ish machine learning paper on top of his out-of-core algorithm. So it's an approximate SVD. There we go. And here's the graph for it. This is using other Dask Array functionality. He was able to compose a lot of these things to make even larger, weirder graphs. And this runs very quickly. This is, I think, one of the better parallel out-of-core SVD algorithms I've seen, if not maybe one of the few. This is an example of something that I really like. Someone who wasn't me used Dask to write down a complex algorithm. And maybe all of you should do the same in your own fields. I'm around all weekend. I'd actually love to work with people on this sort of thing. Okay. So the goal is to be able to write Dask as a tool to these more custom workloads. Okay. So this notebook talks about many of those things. And I encourage you to look through it. There's also sort of a more explicit spec here if you want to dive a bit more into things. Let's see. A good exercise here that I actually recommend doing, although I'll maybe we'll take a 12-minute break. Assumption that we're going to work on this for a few minutes, or maybe a 10-minute break. We'll go from 8 to 10. This exercise, here's reading a bunch of pandas data frames, computing the length of each of them, and then summing up a length. Okay. So this is, I think, something you might do, just see how many lines are there in this CSV file. Okay. Pandas read CSV actually takes up a bit of time. It's not a trivial computation. And so the goal is to rewrite this computation as a Dask dictionary. Okay. And there's a little start to it here. Okay. So see if you can rewrite that computation as a dictionary, and then execute it, and see if you get faster or slower. So let's take a 10-minute break. Let's come back here at 30 past the hour, at 4:30, and do some time working on this problem, do some time getting up and stretching and doing jumping jacks as you prefer. Again, we're thinking about sort of the core of Dask at the moment. And again, you could ignore all of this if you choose to. This will not be essential. In a few minutes, we're going to go back to data frames, which will be more fun and high level. So the exercise was to take this code up here and write it down as a Dask graph, and then see how well it performed. Okay. So let's look at a solution. So again, we're just moving the parenthesis from the right side of the function over to the left, and we're making some string for our key rather than the actual Python variable. Okay. Here's our solution. Now, if you want to, I need to run, let's run this and that. So with pandas, we can load these 3 files in about a second. Okay. This isn't quite big data. We sort of chose a smallish amount of data just to sort of play with. It's a reasonable size to sort of feel in your hand. And we can execute our graph. We can execute it with threads, and it takes, again, about a second. So even though this workload was parallel, we didn't get much speed up. And that's because of the GIL. So there's the global interpreter lock in Python, and that stops any 2 Python threads from executing at the same time, from manipulating Python objects at the same time, I should say. Now, they can still be concurrent. You can sort of one run right with the other, and so you can trade off very, very quickly. You can sort of run a web server, but they can't actually be active at the same time. Okay? So they're not parallel. They're concurrent, but not parallel. But we can switch. Our graph is independent from threads, is independent from processes. So we can switch and run this with a multiprocessing scheduler, and we do get a speed up. Okay. So we actually do get a speed up on this with one of our schedulers, but not the other. And this is a very nice thing to notice, right? The creation of our algorithm, this dictionary, was completely independent of our choice of execution mode. So we can pick and choose our execution as sort of best fits our computation. If I had a distributed scheduler lying around, I could also execute them the same way. Okay. So in the interest of time, I'm going to skip this. but it's the exact same exercise, except that now we're going to throw in a for loop, and we're going to demonstrate that you can also create these graphs programmatically with Python for loops, with list comprehensions, as you like. So previously, we've been creating these graphs just manually by writing a dictionary piece at a time, but this sort of doesn't cut it for larger, more complex systems. We want to create these dictionaries based off of user inputs, based off of for loops, et cetera. So let's load that and then move on. So a lot of Dask code internally looks like this. We make some dictionary, we have some code in it that does some interesting things, we create the dictionary, and we usually merge those with other dictionaries that we've been building up from doing other parts of our processing pipeline. Okay, so generally, you've learned how Dask graphs work. Dask graphs work. As a reminder, you don't need to know this. This is not essential, but it's maybe interesting to think about. In particular, when you think about arrays, you can also think about, you can inspect those graphs. They're actually sitting right there on the object, so you can think what the graph looks like and you can look at what it's doing. Okay, so let's skip to, do I have slides for pandas? No, okay. So we started with Dask Arrays, high level. We jumped down to the foundations at low level. We're going to jump back up again to Dask DataFrame. So in this exact same way that Dask Array implemented a large n-dimensional array by using lots of little NumPy arrays and sort of streaming through them, Dask DataFrame implements a large Pandas DataFrame, really implements a large DataFrame object, copying the Pandas API by using lots of Pandas operations internally. Okay. So this solves what I like to call the pile of CSV problem, which ends up being pretty common. I heard a nice laugh over there. So if you've run the script, this has made a few small files in your data directory. They're just random account files. They're not particularly interesting. So we have enough data to play with. It's not particularly large. If you feel like actually doing larger computations, if you actually want to work on a terabyte of data, you can increase these numbers. This is the number of files. So if you want 100 files, change it to 100, the data set will increase. It might take a little while. These files will take about 1 second to 2 seconds to run with. So it's a good time to play with. Okay, so we have these files. We're going to call the read CSV function and call the length. So this is exactly the computation that we just did in the last exercise. All right, we just made this graph that called pandas read CSV 3 times, and then called length on all 3 results, and then computed the sum of those 3 results. We did the exact same thing here with Dask DataFrame. Okay, so Dask DataFrame just made the graph that we just made in the last exercise for us. This is the role of the collections, it's to make dictionaries. Okay. Let's just look at that for a moment. df.read CSV, file name. Let's just look at the graph. Dask DataFrame. So it's a bit more complex than the graph that we made, but the essential elements are still there. There's still a call to, pandas read CSV. I guess that's hidden here. It's in this partial. There's, some file name that we're going to read from. It's a little bit strange here because we can need to parallelize within one CSV. You need to sort of block it up and play with different pieces of that file. But still, the essential idea, Dask DataFrame operations are just making dictionaries. Okay, they're just a bit weirder. And we can, play our usual tricks of visualizing things, compute the sum and visualize that sum, et cetera. Okay. And look at the graph. Great. Okay. So one might ask the question, well, when would I use pandas over Dask DataFrame? The answer is that you should always default to using pandas. Pandas is better tested, is better documented, it runs quickly, it has been sort of bulletproof tested. You should only switch to Dask DataFrame if your data sets do not fit comfortably in memory, or if you want some parallelism in some cases. Even then, you should think about other things first, like how do I encode my data frame? How do I use categoricals? How do I store my data on disk? There are many things you should think of before using Dask DataFrame. Please don't use Dask DataFrame. Most of the time people come to me and say, oh, I'm really interested about parallelism. I think, wait, no, you actually don't need to do that. You just need to use pandas better. So that's my disclaimer. Okay. Dask DataFrame is very new. So Dask started, as Jake mentioned, Dask started as a very new project. Dask started in last December, around Christmas time. Dask Array, I would say, is fairly solid now. Dask Array is used, the bug reports, we still get bug reports, but they're very strange cases. Like, oh, this weird part of slicing has this weird bug in this weird case. Dask DataFrame was born a couple of months ago, and it still hasn't been used as aggressively. It's still, so the bug reports are still large things, like read CSV doesn't work with nrows. Just sort of general user beware. That being said, if you have a large pile of CSV files, Dask DataFrame is a great tool. So now that I've added all the disclaimers that I can, let's play with Dask DataFrame. Okay, so as an exercise, this exercise is really just intended to teach you that Dask DataFrame looks and feels like pandas. Okay, and so the exercises here are going to be pretty much just pandas exercises. So if you're in the previous tutorial by Tom, or if you're just sort of familiar with pandas, these should look very familiar. So we can, for example, compute the mean of a column. Oh, we should actually look at one of these data sets. Right. So this data set is a bunch of accounts with credits and debits into maybe a bank. Every record has a user ID, which is a number, a name, which is a string, like Alice or Bob, and an amount, a positive or negative amount. And there's 300,000 of these or so. Okay. And so we might compute something like, again, the mean of the amount column. And we're just going to use basic pandas syntax here, df.amount.mean. The one extra bit we need to add is this call to the compute method at the end. Okay. So let's take a minute and do just basic pandas operations. If you're not familiar with pandas, I highly recommend looking at the pandas documentation. It's a very good use of this minute. And if you are familiar with pandas, this is just to encourage you and sort of satisfy you that Dask DataFrame looks a lot like pandas. So let's do that for 60 seconds. Okay. So these are my solutions. I wrote them out. I hope they're all correct. I've played with Dask DataFrame for no longer than 2 months or so, since that's about the age. And I'm also fairly confident in all of these answers, because I played with pandas for the last year or two. And so let's run one of them. This is, well, let's do a simple one first. Use the drop duplicates method to find all of the distinct names. Right? So I'm going to call df.names, get out the names column, call drop duplicates. That'll give me sort of a distinct or unique result, and call compute at the end. It walks through all of my CSV files, reads through all of the text, parses everything, and then gets a bunch of little pandas data frames. On each of the pandas data frames, it computes the unique names, merges all those together, and does another unique on those. And we got our nice list of names here: Alice, George, Tim, Zelda, etc. Okay. And we can go on. And so for a subset of pandas, I want to emphasize subset there, Dask DataFrame does everything as you would sort of naively do it with these for loops. Okay, So let's move on. Okay, so that's how dask.dataframe is sort of the same as pandas. A couple of extra things. We don't get as much parallelism with pandas as we do with NumPy, because NumPy releases the GIL fairly aggressively. NumPy works very well with threads. If you don't know what the GIL is, don't worry about it. NumPy is designed to work with many threads. Pandas is not. You can use dask.dataframe with a multiprocessing scheduler. Things get a little bit weird sometimes, though. It's not always better. However, Jeff Reebok from Pandas has been very gracious in releasing the GIL in a lot of operations very recently. So operations like group by operations and factorize are going to be released, are now released in master. So you'll get actual parallelism, and that'll be in the next release. And if anyone has an operation in Pandas that they'd like to be fast in parallel, you should use dask.dataframe, use the operation, see you're only getting sort of 150% CPU usage, and then raise an issue. I think Jeff has actually been very, very gracious about releasing operations that he knows people need to be released. This is actually where you all need to do some work and try this out and generate use cases where we can identify where the bottlenecks are. Yeah?
Does releasing the GIL affect the determinism of the result, like if it involves random numbers in the seed?
Yes, the question is, does releasing the GIL affect determinism? Is releasing the GIL safe on my Dask? The GIL is the global interpreter lock. And locks are actually used for a good purpose, right? Locks save us from problems. And so when one releases the GIL, one needs to be safe about it, and that's a lot of the work in releasing the GIL. Additionally, you're asking questions about, let's say I call NumPy, let's say I call it Dask random, and there's two operations that might be running in parallel. How do we know that those aren't sharing some shared state that we're not aware of? We need to be careful about that too. And so, for example, Dask Array random uses the NumPy random state object. So we think about these things. They come up, and we try to ensure that our algorithms are correct in parallel. If they're not, please raise issues. But it's a great question. Parallelism is dangerous, I think, is maybe the main takeaway from that, and that one needs to be safe. We try to be as safe as we can. If we're not, please raise issues. Okay, so that was dask.dataframe is like pandas. Here's how they differ a little bit. This is maybe more interesting for core developers or experts. So pandas has an index. We might index our data by a time series, linearly throughout the year. Dask.dataframe needs to break up your large data set into many smaller data sets. Okay? And it needs to do so in a way that it sort of is intelligent about it. So we might, for example, break up your date time index by month and have one partition that we load into memory at once is for January, one is for February, one is for March, one is for April. Okay? And so on top of the index, Dask.dataframe maintains something called divisions, which is the locations in the index on which we're separated. Okay? And these divisions allow us to do algorithms much more intelligently. For example, things like the loc operation in pandas, which allow you to do sort of range queries. The divisions let us selectively load data that we know are relevant and not load the data that we don't think is relevant. Operations like joins and group bys along the index can be much faster because we know all of the similar data is aligned together. So divisions and the index play a big role in parallelism, play a big role in performance when your data is on disk and when accessing your data randomly is hard. Okay. So this is maybe one of the bigger design changes in Dask.dataframe on top of pandas, this addition of divisions. So if we look at just what comes out of a CSV file, divisions has no information in it because CSVs we're not aware of how they actually break up easily. There's no index information there that's obvious that we can trust. But if we set the index, let's say along the names column, this is doing an on-disk shuffle, which takes a little bit of time. And our data set has been divided, it's been sorted along the index. That's what the shuffle was for. And it's been divided across different ranges of names. So we know that everyone from Alice to Ingrid is in the first division, in the first block on disk now. Everyone from Ingrid to Ray is in the second block on disk. And everyone from Ray to Zelda is on the third block on disk. And now if you do, say, group by operations, we're actually ensured that all of the Ediths are in exactly one of the divisions, exactly one of the partitions. And so we can do things like group by operations, knowing that all related data is in the right place. We don't have to sort of go between lots of our different pieces. Okay. And so when you think about performance on data on disk or in parallel in general, your data is likely going to be partitioned if you want it to be fast. This isn't restricted to Dask DataFrame. Many on-disk systems will try to partition your data if you let them. Large databases like Hive or Impala, public systems like Parquet will try very hard to partition your data. This is very important for performance. And when you sort of start using Dask DataFrame to get actual performance out of it, this becomes very important. Okay. Divisional is used for things like this, and we can see that our data set is now sorted along one of these indexes. Okay. This is, however, an expensive operation. You don't want to do this all the time. You want to do this roughly once if you can avoid it. And ideally when you ingest your data. Okay. And things like we can get loc off of Edith, and divisions has changed. We know that we're just completely bound around Edith now, and we can get just Edith a little bit faster than we would normally otherwise do. Okay. Okay, so exercise. Use the setIndex function to index on the ID column, and then find the user with the 100th ID. Also check divisions and see how Dask partitioned your data. This should take a line or two of code and a few seconds of computation. Question?
Do you have any plans to implement the df.query method?
What does the query method do?
It's like, it's similar to doing df and then brackets, df.amount less than 0, but you would just do df.query and then inside a string amount less than 0. And that's a method that...
Yes, the question is we intend to implement the query method. Is it where? Is it called where by any chance, or is it query?
No, it's just called...
It's called query, okay.
Yeah.
Yeah. That would be trivial to do. That's probably 10 minutes of time. Raise an issue, and it'll get done within an hour of when I can sit down, or add it yourself. Yeah, I mean, the Pandas API is huge. I've implemented things that I sort of see used often, but there's lots of things that aren't. And a lot of what we need is people to use this, report back what's missing. These things are very easy to build, but there's 1,000 of them. And so we want to find the 100 that are actually important. And that's what we need questions like this for. Okay, so moving on. I also note that this query of this 100th element is actually sort of slow. It's not as fast as you want it to be. This depends also a lot on disk storage. Because Dask DataFrame is going to read from your data from disk every time, it's actually on this data set, it's far slower than Pandas would be, right? And when you think about large data sets that are bigger than RAM, we start to have to really think about efficient storage. Something that you really need to start thinking about if you want to go bigger than RAM on disk. The next notebook will be about that. Before that, I want to sort of point you to this bit on limitations, things that don't work. This actually plays great into your question. The Pandas API is huge. It's also like NumPy is sort of this beautiful jewel of a library, the API. It's very clear. There's sort of 20 things, and that's sort of all you need. Pandas is this sort of humongous Swiss Army knife. And so please report what you want. Come bug me and say, hey, I really need this function. And in the case like query, it's, again, trivial to implement. I just need to be told, or we need to be told, or we can work on it together. Here's a list of things that definitely work, and a list of things that don't work. Okay. So moving along, I'm out of here at 5:20. Is that accurate? Jake's sleeping. 5:20, right? Yeah. Thank you. Okay, so I'm going to talk briefly about data frame storage. And generally, this is a lesson that parallelism and on-disk computation don't come for free. You actually need to start thinking about things differently, a different set of things. In particular, CSV files are very slow. and you don't want to read from CSV files every time you do any operation. With pandas, we take a CSV file, we would load it into memory, then we do lots of things. Right? We no longer have that luxury. Right? If we have the luxury, then we should keep using pandas, sort of running on the assumption that we can no longer fit that thing into memory. And so now every time we do any operation, we're pulling from disk. And that very expensive operation, reading from CSV files, is with us with every trivial operation we want to do. And for that reason, we need to start thinking about binary storage and other kinds of storage, column storage, categoricals, nice encodings, compression. These are all terms that if you want to get nice performance out of large-ish data, you should become familiar with. So I'm going to blow through this fairly quickly. So we have our data set. We have our CSV data. A lot of the sort of typical methods that you find in pandas, like toHDF for HDF stores, are around. There's an error with Mac, or with the recent version of PyTables. I think Tom found this recently. But if you switch back to a slightly earlier version, everything will work fine. Things like HDF work fine. But if you actually look at the time to, so HDF5 is a nice on-disk format to store binary data. It's very good for ints and floats. It's not so good for strings, at least in interacting with pandas and NumPy in the Python system. And so in a data set like what we have, with strings in it, CSV and HDF5 actually are about comparable. Neither one is particularly faster than the other. And so these strings, these object D types, these names, Alice and Bob and Charlie, in our data set are actually destroying our performance and stopping us from having nice interactive use of our large data set. And so there's some things we can do. We can store our strings as categoricals. And I'm not going to explain these. I'll explain them a little bit because they're valuable. And dask.dataframe has nice methods to categorize distributed data frames or parallel data frames. And we can get a bit faster here. So it used to take about a second. Now it takes about 350 milliseconds. So what did I just do? I just ran through a bunch of cells. So categoricals are a way to encode text data, frequently recurring text data, as numbers. So for example, Alice might be 1 and Bob might be 2. Then we can store those numbers efficiently on disk. And we can store just a very small index mapping Alice to 1 and Bob to 2 in a much smaller space. This allows us to encode data like names much more efficiently. So let's pull off. This is a pandas thing. This is not a Dask thing. It's just important enough that you all should be very aware of it. Everyone should be aware of it. So we have this. So let's just pull off a little bit of data, and this will just be as a pandas data frame. This is a pandas thing. Okay. And let's look at the names column now. And so names is this weird object now. It looks exactly like what we had before with these names in there, but it's of type D-type category. So it looks and feels exactly like a normal pandas series, but internally, a.names. But internally, those values are actually stored as numbers with one index of the ordering of all of those numbers. And so we're able to store our names column now as 8-bit integers on disk rather than as these serialized strings. So this is completely separate from Dask. This has nothing to do with Dask. It's just an efficient encoding of text in memory or on disk. And I'm bringing this up now because it's very important when you start thinking about disk storage. You have to start thinking about encodings and how you're going to store your data. There's a question. Yeah, so we're using the toHDF function method inside of pandas. And the pandas HDF store does its own thing on top of HDF5. So if you read this with H5Py or with your HDF5 library in C, there'd be some other junk in there. But from pandas to pandas, people tend to like it. Okay, so I've run through a bunch of code in a way that it's probably hard to follow up here. It is all in your notebook. There's also a nice blog post on how to use categoricals and why they're important. I recommend looking at it. The main message I want to get across is that on-disk storage becomes important when you start wanting to use disk. One mechanism to make that fast is to use categoricals, or to think about encoding, how we represent our data on disk. And strings end up being a real pain point for the Python ecosystem. Another thing that comes up is that, when I'm doing this computation up here, I'm actually computing on the amount column, not the names column. Like, why was it even important how I stored names? That's because by default, people tend to use HDF5 in a way that stores them sort of as a row store. There's a name stored and then an amount stored, and a name stored and an amount stored. And sort of we're forced to load in the whole data set at once rather than just a column at a time. And so another sort of very nice thing for performance, especially when dealing with disk, is a column store. We store our columns in distinct regions on disk, so we can pick out just the columns that we need. There's this tiny little library called Castra. It's a few hundred lines. It's a collaboration between myself, Phil Cloud, and Valentin. I'm forgetting Valentin's last name. Hey, Valentin Halem, yes, thank you. It's a tiny, tiny project that was just meant to demonstrate as a prop the ability to think about compression, encoding, and performance, and get nice performance out of it. So here, using categoricals, we're able to get 300 milliseconds, which is much better than the second we had before. I'm going to use a sort of tiny on-disk data structure. I'm going to put it into Castra, which is something like HDF5, but a little bit different. And we can get now much faster reads out of it. So Castra is a columnar, a column store that is also partitioned along an index, thinks about compression well, and it handles encoding of categoricals well. These are all the things that I sort of needed when doing some small experiments. It was a few hundred lines of code, and actually really made me feel very positive about custom data stores. It actually was not hard to build. Let me, one more second. And it gives us query times that go from being seconds to being hundreds of milliseconds. Or if you're doing range queries, also maybe even faster. Which turns things from being sort of bulk data time to maybe even interactive time. And again, this isn't a hard thing to do, right? On your data set, we needed to say this toCastra function and provide categories that we cared about. So Dask provide nice mechanisms to use these interesting data stores. Okay, this question?
How does bcalls relate to Castra?
Yeah, so bcall is another great on-disk columnar data store. Actually also run by Valentin Haenel, along with Francesca Alted. Bcalls is much more sophisticated. It handles appends in a much nicer way. It thinks a bit more about compression. The main difference is that Castra is partitioned along the index, much in the same way that Dask is. So we have, rather than knowing the first 1,000 rows, the second 1,000 rows, we know January to February. So we're indexing based on value rather than based off of location. And so it's a very good fit for Dask. It's also much simpler. It's, again, a few hundred lines of code. It's pure Python. It's fairly simple. It handles categoricals well, which is something that I found was very important. Yeah, those things. It's just a very small, simple project to do exactly what this needs to do. Bcall is another great column store. There's a from bcalls method on dask.dataframe 2, which you should also use. It's a great thing to do. Okay, there's an exercise here, which I'm going to skip, which has you use setIndex to make an index, and then toCastra to store that data set in Castra. And then Castra also supports efficient range queries along the index. So you can pick off just the pieces that you need. It's a nice combination. So when I play with data sets, I usually go through this sort of this routine. I read in my data from whatever store it's been given to me, often the pile of CSVs. I then set an index, and that takes some time as there's this sort of efficient on-disk shuffle operation that occurs. But that sorts my data along an index that I'm going to be querying against often. It's usually a date time column or ID column, something that's very important for my normal queries. I'm going to shove it into some on-disk data structure, like Castra. Or maybe there's a good talk by the Dado folks later on about S-frame. So another they also think very hard about thinking about compression, about blocked access. And if you think about these things well, again, you can achieve much, much better performance than reading from CSV files. Please don't use CSV files. You'll be so much happier. It really is wonderful. And then I perform queries off of it. So this recipe is one that I recommend. Here I'm using Castra, this sort of experimental thing. Please don't use Castra in production. It's very new. It's maybe not even going to be maintained, but it's a good example of what you can do if you're smart about encoding blocked access, partitioned access, column stores, and compression. And these end up being very important if you want to run from disk. Just like Dask Array asked you to think about chunk sizes, dask.dataframe asks you to think about on-disk storage. That's the trade-off. So we need to sort of add onto your thinking. OK, so we were high level, then low level, then high level again. Now we're going to go low level again to imperative programming. And this is, sorry, first, any questions about dask.dataframe before I jump to a completely different topic? Yeah.
This is not about the storage part, but what Dask database in general. But I'm a little bit confused because when you started with NumPy, you were starting with this massive array on disk, and you collapse that into a scalar. Whereas here we have this logically massive table of disk, and the performing operation was still remaining in the table space. So when you do, for example, remove drop duplicate, it runs the whole computation, shows you the head, shows you the tail, and shows you the count, I think. And then when you do something on top of that, it has to repeat this computation and do the new one. So it's building up the chaining. Computations to represent the frame. Is that how it works? So every time you add something, you're just adding a new node to the computation cloud frame, which you read on each time.
Right, so I'm going to summarize your question. Sort of generally, what happens when we do sort of an interactive workflow with dask.dataframe with things like drop duplicates or with other things. And so in the case of drop duplicates, we're going to load up one part of our data set, do drop duplicates on it, a distinct. Hopefully it's now much smaller, in the same way they had scalar with Pandas, with NumPy. Load up another thing, make it much smaller. Load up many of them at the same time, do it in parallel, get lots of small pieces. In the case of dask.dataframe, then it's going to bring all the pieces together and do another drop duplicates. That's the current algorithm. That can probably fit in memory. Now we're going to do something different. We're actually going to do that, but then some other thing instead along with it. Now, if we computed our results, if we actually wanted to see the results, we did all that computation. We evicted intermediate results from memory very aggressively. We saw the results on our screen. We now do something slightly different, and we're forced to do all of those same things again. So every call to compute will trigger a complete computation of everything in your graph that's necessary to compute the result. And if you call compute many times, you'll be recomputing all those intermediate results many times. This is bad for interactive workflows. Something that I'd actually be very interested in, sort of my next thing to think about deeply, is opportunistic caching. Can we find intermediate nodes in that graph that were expensive to compute, are cheap to store, are frequently used, and were recently used? And if so, can we devote a couple gigabytes on memory and maybe 50 gigabytes on disk? And how effectively can we use your system for these sort of interactive workflows? But as written, none of the Dask schedulers solve that problem. But interestingly, once we add it to one of the schedulers, all the high-level collections and any other custom code will be able to benefit from that. Does that answer your question?
Yep.
OK, great. It's a great question. Interactive computation on disk is a hard problem. I think that opportunistic caching is a good solution to that. But there's probably other good solutions. OK. We have two topics to talk about, and I have 10 minutes. We can't cover both of them in depth. I can either cover one of them in moderate depth, either one, or we can cover both of them in lightning speed. So we have three choices, and the choice is yours. We have cover low-level stuff in depth, cover high-level stuff in depth, or cover both shallowly. Show of hands for low-level stuff in depth. OK, I'm getting a fifth of the room. High-level stuff in depth. I'm getting, I think, a majority. And then everything shallowly. Ooh. Okay, runoff election. High-level stuff in depth. Shallow. I think shallow wins it. Okay, I just burned a minute. I'm also going to start talking really, really quickly. Okay, so imperative programming. We're going to do both of these roughly 5 minutes each. Imperative programming, this is also, I'm going to call it dask.do. It's a do function. This function allows us to create custom graphs, like what we did in the second notebook, but without making a dictionary. So the goal is to do sort of these custom workloads, but not force people to write dictionaries. That was the goal. This came out literally last week. No one's used it, but I would like people to try it out. That's why I'm talking about it here today. I could really use some feedback on the interface, and I want people to see if it's useful or not. So what we're going to do is whenever we would normally call a function in Python, we're going to wrap that function in a call to do. And that will instead start building up a Dask graph for us. So we can still use all of our Python tricks. Our IDE will do completion, et cetera. But we won't actually do f. We will delay it, and we'll add it to a graph. So in our familiar example here, we have these functions, inc and add, and we have this Python code that runs sequentially. And we used to make this dictionary, and this was interesting, but maybe not for everyone. And now we're going to write that like this. So it looks very much like our Python code, but we put do in a few places. We've annotated our code. Okay. And this makes something that we can run in parallel. And it makes this dictionary that's very much like the dictionary we used to have. Okay. So do is a mechanism to create Dask graphs, custom Dask graphs, not Dask Array or Dask DataFrame stuff, but the dictionary things, using Pythonic code. Okay, so we had this exercise where we were going to call pandas read CSV a few times, and then we're going to, the exercise is to turn this into a parallel code. We did that before by using Dask dictionaries, but we're now going to write it, let's just do this right in here. So A, B, and C are now these sort of token objects. They're going to be evaluated eventually. Calling length on this token object, so that length function will also have to be delayed, because length isn't going to work on these tokens. And then the sum function on all these values will also have to be delayed. So here we go. And total is just this, this weird token thing. Thunk of whatever, however you want to call it. But total has a Dask graph attached to it. And that Dask graph is all of the functions that we just called. This is the thing that we made when we made the dictionary. And total has a compute method. I think by default this is going to use threads, so we should give it a second of time. Yeah, from dask.multiprocessing. Let's get the get function. And you can always specify a different get function, a different scheduler inside. Whoops, need to run that. Here we go. And that happens a bit faster with the processes. So instead of making this dictionary, we annotated the functions that need to be delayed with do. Sometimes there's functions you don't want to delay, like control flow. If you want to have sort of if statements in there, for example, what's going to all happen. Again, I write a blog. You all should read it. It's, I think, absolutely wonderful. But here's an example of a machine learning guy had some cross-validation code. And this is the sequential and the parallel version of it that flip back and forth. And there's just a few calls to do in there. Okay. So this custom algorithm, for loops, very sequential looking. Think a little bit about your algorithm, about what can be parallelized, what needs to be delayed. But the actual coding changes are very slight. Okay. That's do. There's recent work by Jim Christ. Okay, that's do. One question on do. Moving on. Oh, one question? Yeah?
Can you override it if you just want to debug parallel at once? I know there's other frameworks that do that, so like always eager or something like that.
Yeah, so always eager, I mean, you could just make do the identity function, and that would work. Also, I want to just also point out, Yeah. I also want to answer a question that wasn't at all your question, but is a question that you remind me of, which is that there's all these different get functions, right? And there's this really nice one from dask.async import get sync, which is a synchronous scheduler. This is not parallel at all. There's no threads, there's no processes. At some point, you're going to write a program with Dask that has a bug in it. And that bug is going to be deep inside of some scheduler call. And so it's very, very nice in these cases to run not in parallel, not in processes, not in threads, but just in your local thread. And so there's a synchronous scheduler, get sync, that does that. This is amazing for debugging. You can set it globally. There. Now all of my computations will be run in a single thread. Debugging is much easier. It's not eager like what you were asking for, but it's OK. There's a great issue on Dask Array about eager evaluation of Dask arrays. And I think we figured out a way to do that. So if you want to chime in, that'd be great. OK, shallow coverage of the high-level topic. Dask bag. Abstractly, a list is an ordered collection allowing repeats. A set is an unordered collection not allowing repeats. A bag is an unordered collection allowing repeats. It's kind of like a list, but we're not going to guarantee order. That's the definition of bag. Dask bag looks a little like PySpark, if you're familiar with that. It also sort of copies the PyTools interface, if you're familiar with PyTools. Dask bag is roughly PyTools plus multiprocessing. Okay? It's very good for dealing with JSON data. Okay. So what do I mean by that? Here are a few ways of constructing a bag. Let's just take this one, b dot. Let's take a few elements. Oh, S3 is slow. OK. Reading from the internet is slow. Sorry, I'm figuring out what I need to tell you guys. Right. Here's really the common use case. dask.dataframe handles the pile of CSV files pretty well. Another common pain point is the pile of gzip JSON. Show of hands, who has piles of GS.json? Yeah, isn't it great? Most of your time interesting in this data is spent decompressing and deserializing. It's a really terrible format for storage, for computation. So we're going to get a bunch of JSON files that are on disk. There's about 50 of them. We're going to load them up into some bag, and we're going to take a few of them out there. At the moment, they're just text. There's all these lines of text coming from our file. It's not very interesting. So we're going to map the json.loads function onto our big bag of text. No, we got lots of nice little dictionaries coming out. And again, if you're sort of familiar with PySpark, you think that this is sort of PySpark's dumb younger cousin. That's very easy to pip install and run on your machine, and runs in a pure Python processes, and is sort of very lightweight. I have used this on a big, heavy machine with 30 cores to shuffle a lot of data on disk efficiently, and I have beaten Hive on like a 10-core cluster. I also really think that the single machine is a great computational target. So we're going to play very quickly with this JSON data. We're going to filter out everything. We're going to get all the Alice commands, all the Alice records. And what do we have here? We've got an ID, we have a name, we have a bunch of transactions. So it's a sort of nested document structure. It's kind of like our CSV file, but it's nested in this strange way. And we're going to just use some Lambda function in there to pull out all of the records where the name field equals Alice. Okay, and we're going to take a few of them, 5. And this all happens very quickly. This is using both the sort of streaming elements that you'll find in PyTools or just general Python iterators, along with the multiprocessing elements you'll find in multiprocessing. Along with nice serialization, you'd find a project like Dill. And we can do some interesting operations. We can count the number of transactions in each record. We can pluck out just the count column, and we can compute the mean. And now that we're not just taking 5 elements, we're actually taking a bunch of them. Oh, that already ran. And so now, where before we used to have one process that had 400% usage, we now have 4 processes at the 100% usage. Because we're limited by the GIL in these operations, we're using Python, so we have to use multiprocessing. Okay. So there's other operations there. Sort of the things you'd expect to find are there, if you're familiar with these sorts of projects. Dask bag was really easy to create. And again, all it's doing is just making dictionaries. So yeah, here's a bunch of tasks in that dictionary. So with that, I'm going to switch to my ending slides, which are somewhere over here. Oh, there's also homework. We don't have any interesting data sets to give you, because I can't give you guys all 10 gigabyte data sets to play with 100 gigabyte data sets and have you all download them and not kill the world. But this notebook has a lot of links to data sets that I have found interesting when playing with Dask. They're all publicly accessible. You should not download them on conference Wi-Fi, please. But they're all quite fun. And there's some interesting blog posts are linked, and there's some good stuff there. So again, this is all on the repository that you have. Some ending remarks. OK, so Dask is a library for parallelism through blocked algorithms and dynamic task scheduling. And hopefully those two ideas now make sense to you. And if nothing else, that's a value gain from this tutorial. Those are good tools to think about when dealing with medium to large data, or very large data. Dask has some high-level collections that mimic Python libraries. They actually just use the base Python libraries that you already know and love. But they use them in parallel and clever ways. It's very lightweight. You can pip install Dask. Dask is actually included in Anaconda. You might already have Dask without asking for it. Dask itself is pure Python, standard library only. The various collections have other dependencies like NumPy and Pandas, but it is very lightweight. You can give this to a student, and they will not have a problem installing it. Really core libraries like X-Ray or scikit-image don't mind depending on Dask. It was really designed to be core infrastructure. Okay? So it's lightweight. You can pip install it. It's cheap. It's good not only for these sort of high-level operations, but also for custom algorithms and dynamic task scheduling. I have personally found it in sort of projects I've worked on to be very useful for the data set under a terabyte case. I think that I find a lot of people overusing large parallel distributed systems once they run out of RAM, and that I think is a mistake for productivity. I think if you're less than a terabyte, I think that you should consider single machine shared memory parallelism. Okay, that being said, you probably shouldn't use Dask because most problems are small. If Pandas will do, please keep using Pandas. And Pandas usually will do if you're a little bit smarter about using it. Also, don't use Dask because you should probably be using a database. Most problems we dealt with today can be solved with a database. In particular, these sort of very unsexy technologies solve pretty much every problem we've mentioned today, the sort of weather example excluded. Oftentimes, people come to me or someone else, and they say, the Pandas is running slow, run the CSV files, can we use parallelism to make it faster? And we can, but usually the right thing to do is just to point you to Elasticsearch or to Postgres. These are usually much more solid technologies that you spend a little bit of work can make your computations pretty fast. We didn't talk about distributed scheduling. That exists. Love people to play with it. Diagnostics, things like profiling. Dask has a great parallel profiler that's really good to analyze parallel algorithms. We didn't talk about the details of dynamic task scheduling. That's a really interesting topic that I think other projects should think about. We also didn't talk about that much about what breaks. If you go actually out the bottom of most of those notebooks, there are limitation sections. And in most of the documentation, we're pretty honest about what doesn't work. Dask, again, was written starting December, around Christmas time. I was literally like in my family's home on my couch making a matrix multiply. So it's new. It's moving very, very, very fast. But be aware that it is moving fast and breaking things. So there's a Dask tag on Stack Overflow. Please use it. There's GitHub issues for questions like, does you support query? If you add that to Dask issues, we'll implement it very quickly. I've actually in the last week or so, I've had about a 20-minute response time, which I'm very proud of, during working hours. We use the Blaze DAF mailing list. Dask grew out of the Blaze project. Phil Clow is giving a great talk later tomorrow, I think, on Blaze. You should check it out. And also, I'm around all weekend. I would love to talk to you about trying to get you to use some of these tools inside of your workflow and make users out of you. So that's it. I'm over time. So thank you guys for questions. Thank you guys.